All right, hello. Today didn't go as planned with a lot of my classes. We had a power outage here for a few hours, but luckily we're back on now. So I hope this works in people's schedule. This is when we would normally be in Wednesday class, and I want to hopefully answer some questions, work through some problems on a piece of paper here. I'm just going to get set up so you can see what I'm writing. You don't need to look at me, but I'll set this up so you can see what I'm writing. And you can use the comments here to put questions in. I'm keeping an eye on the video, so you can put some comments in if you have particular questions you wanted to ask about from the homework or otherwise from these topics. So I'm trying to flip this around so you can see the piece of paper, and we'll work through some examples anyway, and whatever questions you have. Hold on. So welcome. I'll be keeping an eye out for the comments here. See, we have a couple of people on already. This will, of course, be available. I mean, I'll leave it up on the channel here. If people link into it later on, you can watch what we went through later on if you don't get to be part of the stream now. But it looks like we're up and running. So say hello here, and we're going to work some exercises. 6.1 in the textbooks where I'm taking these from, you've got some videos that are worked out in the videos in XYZ homework. I do not have everybody signed into that yet. I mean, I'm getting just checked in on the roster there, and there's quite a few of you that haven't gotten into that yet. And that's really going to, the primary thing that's going to have to take the place of our class time, because I don't expect everybody to be on that many hours or have the bandwidth for that. But working with the XYZ homework and the resources that are there are going to take the place in most of the lecturing, and should tie right into the homework exercises that you're working through there. I'm going to do some other problems from here now, but 6.1 from the book is where this stuff is introduced. Exponential functions. So we're used to doing things like 5x cubed, things like that, with exponents being a number and your input going in as the base. Right, your input of the function is the x, which is down here. That's what we're used to dealing with. Those are just regular power functions. Exponential is when we do this the other direction. So an exponential function would look like 3 to the x. And so the input is actually going in as the exponent, 3 squared or 3 cubed or something there. That's the kind of functions that we're dealing with now. The same laws of exponents apply that we've always had in algebra, but they look really different now that the letters are up here. It takes some getting used to, and that's what we're trying to get into now, is doing some calculations with these, thinking about what the graphs of these look like, and eventually going to be solving equations using this kind of function. So I got some weird looking questions to start with, and I'm going to do number 11 on here because it's kind of the weirdest of this set. It says to evaluate each of the following. For number 11, we're asked to evaluate f of -2 over g of 1. Of course, we need to know what these functions are here. This is referring to the functions f and g, which are introduced in this problem, in this set of problems. And they're exponential functions. F of x equals 4 to the x. That's exponential base 4. And g of x is 1/3 to the x. We're going to have strange numbers for the base sometimes. We're going to have to deal with that also. But since the power is where the input goes into the exponent, that's an exponential function also, different base. So evaluating this would be substituting these values into the function and working out what you get. And the values, of course, go in for x. So if f of x is 4 to the x, then f of -2 is 4 to the -2. And we're going to have to think about what that means. And then g of 1 is 1/3 to the 1. Regular exponent rules tell us that something to the first power is itself, so that's just 1/3. Negative exponent rules tell us something about this. If you have 4 to the negative 2, that's the same as 1 over 4 to the second. That's a familiar exponent property. So we're getting back into these. These are both fractions. That's 1/16 divided by 1/3, or here we go with the evaluating part. I'm just going to work this out. Dividing by 1/3 is times 3 over 1. So I got 3/16 for the value of that expression. That's what I end up with from the evaluate problem. All right, so that's number 11 from there. That's just doing evaluation, getting used to how these functions work a little bit. If I take something like that, that's actually going to be one of the homework exercises here is to graph y equals 4 to the x. What does this look like when you do the graph of it? We should think about a table when you do a graph, plot some points, and get used to how this looks. If f of x is 4 to the x, then we could substitute some different values in over here and see what happens for y. Those are going to be points on the graph of it. So if I start with some easy numbers, I can work through that. 4 to the 0 is just 1. That's what the 0 exponent does. 4 to the 1 is just 4. 4 squared, that's 4 times 4. So we're getting really big pretty fast. 4 to the third, be multiplying by 4 again. I'm going to get really big numbers right away. So that's what happens with exponentials. As you go out the graph, you're getting higher and higher powers. If your base is bigger than 1, that means you're multiplying by it over and over again. So you get really fast growth. What's called exponential growth. A lot of times people use that expression for something that's growing really fast, that it's growing exponentially. This is literally growing exponentially. We saw unfortunate examples of exponential growth over the last few days in this. If you've been tracking these virus numbers for a few days, it looked like it was growing exponentially. And since then, it's kind of straightened out to be more linear growth as far as the new cases in our state. Still growing, but not growing exponentially anymore, which is a good sign. Anyway, this one is what I have on this table leaves a bunch of unanswered questions. So let me mark what I have so far. When x is 0, y is 1. And when x is 1, y is 4. And when x is 2, y is all the way up to 16. And this is just growing like crazy out here. So it's really fast growth and getting steeper all the time. That leaves the open question of what happens on the other side on this. And that's what we got to look at now. So if I went back and did negative numbers, let me just jump over to something like -2 for the input. What is it? Well, we did 4 to the -2 already. The negative exponent means reciprocal of 4 squared. 4 to the -2 is 1 over 4 to the 2, or 1/16. So what you're going to get with negative inputs, or x values, is you're going to get fractions like this, which end up really small. If your base is large, these are going to be really small numbers. They're still positive numbers, but they're very small ones. And that's what happens on this side of the graph. -2, you're at 1/16. You're barely above 0. And if I go further out, I'm staying above 0, but barely, right? These are really tiny numbers. This is 1/4 and on up to 1. So 0, 1 is a key point on it. 1, 4 is there because this is base 4. And the rest of it has this kind of shape to it. Hopefully looked at a few of these by now from the either the Lumen work or the XYZ work. It hopefully works with some examples like this. Basic exponential functions look like that, and they go through these 2 points. When the exponent's 0, you get 1, and when the exponent's 1, you get whatever your base is. And it's the basic shape that we're going to be working on with graphs of these things. Trying to get used to those this week, and And then think about this inverse function idea a little bit, because we got to apply that next. All right, you will see this letter E in here also. I'm trying to summarize this as quickly as I can. We got the regular transformations to do, and then we got this letter E showing up. But we're not going to get terribly deep about it, but that's a convenient base that actually is on your calculator. And we want to look at exponentials with base E also. But before we get into that, we got some transformations of the graphs to do. We're going to do a little bit more with the graphing. All right. So still in 6.1 in the book. I'm taking these right out of the regular textbook here. Number 22 says to graph parts A through C on the same graph. So we're supposed to draw the graph of three of these related things. Part A is y equals 3 to the x. Part B is y equals 3 to the x minus 2. You can see how closely related they are. Part C is 3 to the x plus 2. So what do these kind of things do to this function? I want to tie it back to our idea of transformations that we've talked about with other functions, because that still works here. But I also want to think about the laws of exponents some more and how they apply to expressions like that. When do we add and subtract exponents also? So the first thing is the graph. Let me actually solve this question, and then I'll tie in a couple of related ideas about the exponents. Your regular graphing technique for this is it's a base bigger than 1. It's going to have the same shape as the last one that we looked at. The key points to it are 0 and 1 for inputs. When x is 0, you get 1 all the time. And when x is 1, you get the base. 3 to the 1 is just 3. So those are your two key points. That doesn't seem like much to go by when you draw the graph. 0, 1, and 1, 3. But since we know it's an exponential function and we know the behavior, this is really just going to keep going steeper and steeper in that direction and flatter in that direction. They're not complicated graphs. They have this kind of shape to them. If the base was less than 1, it would kind of be the other direction, but this is what exponentials look like. The related ones over here, transformation. So this is replacing the input with x minus 2, replacing x with x minus 2. If you remember, that's a horizontal shift. We're just changing the x values by 2 units over. It's a horizontal shift 2 places to the right. And we do f of x minus 2, like that's 2 places over. So on my graph, that's going to go through 2, 1, and 3, 3. Both of these key points would just be moved to the left 2 places. Asymptote's still going to be down here where it flattens off. It's called the asymptote. That's going to be down here still. And it's still going up like this, but it's moved over a little bit. And goes through 3, 3. Now you could substitute the values in there and see that when x is 2, you get 3 to the 0, which is 1. So you can verify that those points are right. And when x is 3, you get 3 to the 1, which is 3. So you can see how that works with the numbers we got there. But it is a horizontal shift, just 2 places to the left. And this one is x plus 2 instead. That's a horizontal shift 2 places in the other direction. We're going to get 1 when x is negative 2 now. That would give us 3 to the 0, which is 1. So it's going to be over here at negative 2, 1. That's going to be shifted in the opposite direction. Live over here instead. So this is f of x plus 2. This is f of x minus 2. They're a good example for how this horizontal shifting works. So you can really see how that affects the original graph and how that compares. I mentioned the exponent rules with that sort of thing. We have particular questions here, but I mentioned the exponent rules there when we subtract exponents. So let me apply something that we're used to doing in a different way right now. We're used to subtracting exponents when we have to simplify something. If I had x to the 7th over x to the 4th, I think most of you would remember that. You do 7 minus 4 to get 3, right? 7 minus 4. You're subtracting exponents, and that's a division thing. Now we're thinking of this in a different way, partly because the x is in a different place, and partly because we're starting with this subtraction going on up here. But if you're subtracting exponents, that comes from a division problem, or that can be rewritten as 3 to the x over 3 to the 2. I'm just working it in that direction. X minus 2 would be my new exponent. So that expression that we just drew the graph of, you could also think of as 3 to the x over 3 to the 2. It could be rewritten that way. Still, when x is 2, you're going to end up with 3 to the 0, or 1. 3 squared over 3 squared would be 1. So it still fits together. We want to get used to that. We're not used to letters being up in here, and that's really the challenge of this chapter, is getting used to how these rules look. Same rules, different way of using them. Graph is very new. Shape of the graph is very new. But one of the keys with this kind of graph is that they only hit each value once. It can't be negative. Now, 3 to the something is always going to come out positive. It's never going to come out negative. There's nothing down here on the graph. It means your range is only from 0 to infinity for this kind of function. And we're not going to have negatives from the exponentials there. So that's different. All right. The comparison between the different bases is kind of what brings up this E thing that shows up here. So let me do a little comparison here. Hope this is helpful to understand what's going on. So I'm going to put a few of these exponentials on the same graph. I don't need the bottom half of the graph, really just the top half, because that's where my range is. 0, 1 is what they go through, and 1 comma whatever the base is. So if I put a point at 1 comma 2, that's going to be on the graph of y equals 2 to the x. It's going to look like that. I want to compare that to some other bases now. When x is 0, you get 1, and when x is 1, you get whatever the base is, in this case 2. So I only have a couple of different colors, but I'm going to try a couple of different colors to compare this. If I did base 5, it would go through 0, 1 still, and then it would go through 1 comma 5. So that's way up here. That's a lot steeper in this direction. It's growing a lot faster, and it's going to level off a lot faster on that side also. It's a more extreme version of this exponential thing. On the other side, if I did something less than 2, can't do 1. Well, 1 to the x doesn't really count, because 1, no matter what power you get out here, it always comes out 1. That's not very interesting at all as a function. But I can do something less than 2 if I take like 1.2 to the x. That's going to go through 0, 1 still, and 1 comma 1.2. If I'm just a little bit bigger than 1, then it's just coming up a little bit. Still going to get steeper and steeper as it goes out, but that'll be more gradual and more gradual on that side. That's what 1.2 to the x would look like. Still has that same increasing on one side shape, but it's not as extreme there when you're close to 1. That's actually what happens with something that's growing by 20%, or like that'd be awfully high for an interest rate. But if we had be scary. But if we had inflation of 20%, then this is what would be happening to your prices. They'd go up 20% every year, and that would be a gradual increase like that, but it would get steeper and steeper as things got going. Population could do that. If we were in an area where the population was growing, the more people you have, the more potential population growth you have. So you can see curves like this. If it's growing by 20% each year, that's more and more people as you get further out there. The more population you have, the more growth you have. So it gets steeper as it gets higher. That's a characteristic of these graphs. It's important. And in between 2 to the x and 5 to the x, there's a nice graph that has some nice features to it. That's e to the x. And that's going to actually be in between here somewhere. I didn't leave much room for it. Bigger than 2 and less than 5. It's actually 2 point something. There'd be this graph e to the x in there. And that one's on your calculator, and it has some nice features in calculus. So we want to get used to working with e to the x also. E, you hadn't seen an intro to that at all. It's called Euler's number, and it's approximately 2.71. It goes out like this. It's a little bit more than 2.7. Seems like a cumbersome number to work with. It's not for your calculator because you have a built-in button for e to the x and for the number e, but it's got some really nice calculus features to it. So a lot of times functions will be written in terms of that base e when they're exponential functions. E to the x has a slope of 1 right here also. So the height is 1 and the slope is 1. And that's kind of a neat characteristic when we're looking at slope of these things. But that's a calculus question. We don't have to worry about that. We have to be able to do some calculations with that base e also. So there'd be some things to try out on the calculator with that. So you want to evaluate exponential functions, even if they involve base e. That's probably the next thing to think about. So if I have a function like this one's not out of the book, I'm just going to work with an expression like this. 2e to the 4x. Exponent's up here, so it is an exponential function, but it has these extra values plugged in there. 2 and 4, but we want to look at what happens. What is f of -3? Calculating these things, f of 0 and f of 1.4. These kind of calculations with that thing. What happens when x is -3 in this? So f of something means replace the x with that. That's my input now. So this would be 2e to the 4 times -3. Now I can do 4 times -3. I can really do this. That thing means I could rewrite it, but with a value of e being 2.718 something. I don't want to do this. I'm not going to do this kind of calculation in my head. I'm not going to do it on paper either. That's a use of the calculator right there. If you find an e to this something button on there, you can see what that looks like. It's going to be different on different machines. Let me show you one that I have here. Oftentimes it's going to be with the log buttons or natural log things. So I'm going to try this. Hopefully get this visible on camera then. That graph. All right, how do I get out of this? Okay, I don't know how to operate this calculator. Give me a minute. I don't have the right calculator here to do this. I don't know what I'm doing with this thing.
Okay, the CVS one's from home back. It's actually a person.
Wow. All right. Not getting a calculator to cooperate with me. I do this in a calculator instead, but if you have your e to the button, you should be able to do e to the 12. We want to do e to the negative 12, actually. I'm just going to let my calculator do it. I can't seem to get the calculator to work. I don't know. I'll do this on a computer. Just write this down. E to the minus 12 comes out really, really small. Probably will be scientific notation in your calculator also. This is like 6.14 times 10 to the minus 6. If you see something with however your calculator displays scientific notation, that's a really small thing because it's a negative exponent. Those are the values approaching 0 like that. So 2 times that. About 12.28 times 10 to the minus 6, or if I want good scientific notation, I would say 1.228 times 10 to the, make this smaller, I gotta make this bigger, 10 to the minus 5. Okay, so that was a rough one. That's what happens on this end of the graphs here. These exponential functions, they look like that. They get so small on this side that you're going to see really, really small values like scientific notation small. That's still positive, but 0.00000122 something, very small. F of 0 on this one's a little easier. If you put in 0 for x, 4 times 0 is just 0. E to the 0, anything to the 0 is still 1. So that's 2 times 1 is 2. That came out great. 1.4. Try that in the calculator. This is 4 times 1.4. Calculate that part. So 5.6. But e to the 5.6, we need to be able to calculate that. That's going to be a really big number because we're way out here on the graph now. Well, a little ways out anyway. We're going to get pretty big value for that one. E to the 5.6 is already pretty large. I got e to the 5.6. It's like 270.4. So it doesn't take long to get to really large values, and I can go ahead and double that. And those are approximate values there. F of 1.4 would already be up above 500. So these things get big fast. So that works. Now, we're going to kind of set that aside. They're introduced there in a section, and then we go back to some more basic functions because we're getting used to another idea about functions. I want to introduce this inverse idea in a familiar context. So I'm going to think about solving an equation first. The steps you take for solving an equation sort of introduces this inverse function idea. If I have an x involved in an equation like 3x minus 5 over 8 equals 10. All right, so that's not a complicated algebraic thing. We just have x terms and number terms in there. It's not bad. But getting x by itself, we have to think about undoing stuff. I want to get rid of, well, if I have a denominator of 8, I like to get rid of that. So we're used to undoing things when you're working on getting x by itself. And this undoing is really this inverse function idea. This had something done to it, division by 8. In order to get rid of that, we use multiplication by 8. That's an inverse because it gets rid of that, right? So 3x minus 5 is just 80. The inverse of that division was a multiplication. If I want to get x by itself, I want to get rid of the negative 5 next, or the subtraction of 5. So I'd get rid of that by adding 5. Right? This isn't hard equation stuff. That gets rid of that and leaves 3x. We're really using inverse functions every time we do that. Whatever I'm trying to get rid of has an opposite or an inverse right here. Different kinds of inverses. This one's multiplication now, so the inverse of that would be dividing by 3. That's what we're trying to do in this chapter, is think about these inverse things. So I got a value in there. That would be the value for x. That's familiar context in which in setting where we would use it already in regular algebra. The idea of getting rid of stuff. Function-wise, that looks a little strange to get used to the notation of it, but I just said right here, if your function was taking the input and dividing by 8, then the inverse function of that would be multiplication by 8. And then in that next step, the function that subtracted 5, I'll use a different letter for it, but the function that did the subtraction of 5 right there would be undone by adding 5. So the inverse function of that would be adding 5. And a little minus 1 up there looks like an exponent, but it's not. It's a symbol for inverse. It's on a function, so it can't be an exponent. It's not an exponent on a function. It just means the inverse function. That's the symbol for it. And our function, our next function that we did there was the multiplication by 3. It's just taking the input and multiplying it by 3. So the inverse of that, what gets rid of that, is dividing by 3. So the inverse function would be taking the input divided by 3. Those are some simple examples of a function and its inverse right there. I changed letters on these things. I shouldn't have. Let me correct that. This is H inverse, because I called that one H. And the purple one was G inverse, because I called that one G. That's the function. That's its inverse. They undo each other in the sense that if I do one after another, if I do H of 11, I'm going to get 3 times 11, which is 33. And if I do H inverse of 33 now, that's going to undo it. That's 33 divided by 3. I'm going to get back to 11. So if we do this composition, the function and its inverse, we're going to get back the same thing we started with. My starting value is what I end up with after doing that. That's the undoing that we're talking about. That's the concept we're trying to get used to. Undoes a process where it changes the input and output of that. This one had an input of 11, give me an output of 33. So the inverse, when I have an input of 33, I get an output of 11. That's the concept in terms of input and output. So that works well for those kinds of functions. It doesn't work so well for everything. Not everything can be undone with certainty. This one's actually going to be part of the homework, but I'm going to get started on it. 6.2, number 22 is in the homework from this section. Let's spend a little time on this. Number 22 says y equals x squared plus 1. But it says for each of the following relations, sketch the graph of the relation and its inverse, and write an equation for the inverse. If the inverse is also a function, write the equation using inverse function notation. That's a little ominous there when it says if. That means sometimes it's not going to be. And I'm jumping into one of those examples here where we get something that's not a function. So this is a relation. I could draw the graph. Well, it's not an unfamiliar graph, so I'm just going to go ahead and write down the sketch of this thing. You know what the graph of y equals x squared looks like. And if you think in terms of transformations, This plus 1 just moves it up 1. So it's just our regular parabola, except moved up by 1. So that goes through 0, 1, 1, 2, negative 1, 2. These points are on there. 2, 5. These are some sample points on there. So that's a good little sketch of what that function itself does, or that relation itself does. That one is a function. Vertical line test is just fine here. Now the inverse of that is switching the inputs and outputs. So I'm going to do that in table form, and then we're going to put it back on a graph and see what happens right here. Table of those points that I listed, and they're just some of the points on the graph of it. But I got negative 1, 2, 0, 1, 1, 2, 2, 5. That's on the graph of f of x. If I flip those things around, input and output, switch those around, those would be points on the inverse of this thing. The inverse switches the input and output. So if the input's negative 1 and the output's 2, for this one, the input's 2, the output's negative 1. And I can put those points back onto the graph. I'm going to do the graph of f inverse up here. I'll use a different color for it. Let's see what's happening. Where do these points end up? Well, 2, negative 1, 1, 0, 2, positive 1, and 5, 2 is out here. I can do some more points if I needed to, but the shape of this thing is actually going to just be the same as that one, except it's turned sideways right here. We just switched x and y, sort of switched inputs and outputs. And so this thing that used to go up with the y-axis in the middle, when you switch x and y, it goes this way with the x-axis in the middle. Now it's turned around. It's like, I want to picture it this way. It's like I grabbed the x and y axis from here and just switched them around. If I grab those and twist them around, the graph is going to end up down here on the x instead of the y. It's turned around. But you notice on this one, it fails the vertical line test. It's not a function. I didn't really need the whole picture to see that, because I could have noticed it right here on my table. The same input gave me 2 different outputs. That's exactly what can't happen with functions. You can't have 2 different outputs with the same input. So this sort of thing doesn't have an inverse function. It has this relation right here, but I really shouldn't call it f inverse of x, because it turns out it's not a function at all. It's a relation still, but it's not a function at all. You got to see what goes wrong with that. That all we're supposed to do for the problem right there is to sketch the graph. It says write an equation for the inverse. So we're going to do the switching x and y in the equation and see what happens also. Good example on that. If I start off with my original function, y equals x squared plus 1, so f of x is y. I'm going to turn that around. Switching input and output looks like this. My inverse is what happens when you switch letters here. Putting the x where the y used to be and the y where the x used to be. That's the inverse idea. This is the graph of x equals y squared plus 1. Problem with this thing comes up if you try to solve for y. I can get y by itself, sort of. I can get y squared. If I subtract 1 from both sides, I get y squared equals x minus 1. But if you remember, the plus or minus when you do this. You got to realize that I'm only going to get y really if I say plus or minus the square root of x minus 1. I have to do the square root of both sides, and I get that plus or minus in there. Now that's kind of a problem because that means y could be two different things. That's exactly what we saw in the graph right there. It could be plus or minus 1. Like it's two different values. So it's not a function because it's got this plus or minus on output side. Output can't have two different values and be a function. So that's an equation for the inverse, but it's not a function. It's an equation, but it has multiple values right there, so it's not a function. That's the tricky one. You can always switch x and y. If you have something written down that's y equals, you can always switch the letters around. That's not hard. Solving for y is where it might get hard. If you have a simple thing, you can work through that and do it without any problem. But even slightly complicated things like squaring, they don't work out so nice when you go to solve for y. So you might not always be able to solve for y. Well, sometimes you can, sometimes you can't. We have one I see on the homework here, which is possible to do so, but it's a hard one. So I want to get at least started on that. If you try to do the 6.2 homework yet, you're going to run into one where the algebra is pretty hard to do. I'm going to write this down. Number 15, 6.2. It's a homework exercise, but it starts off as f of x equals 4x minus 3 over 2x plus 1. This is going to test your algebra skills a little bit. It says for each of the following one-to-one functions, find the equation of the inverse. Write the inverse using the notation f inverse of x. So it tells you this one's supposed to work and be doable because it says one-to-one function. That kind we're supposed to be able to do. There should be an inverse function. Switching x and y isn't hard. Solving for y is possible on this one, but it takes a little work algebraically. This means my original function is y equals 4x minus 3 over 2x plus 1. And I'm very conscious about changing to a different color right now because what I'm going to write down is a very different thing. When I switch these letters, this is not the same x and y. When we're doing regular algebra steps, we mean that each step is equivalent to the one before it, but that's not what's going on here. We're changing to a very different thing right here. So the x and y there were about my original function. X was the input into my original function. When I change that around, I'm talking about a different x and y. They're switched around now, and the y is the inverse function. And I'm trying to solve for y in this. Getting y by itself. Well, there's y in a couple of different places, so getting it by itself is going to be a little tricky. We can do it. Takes a little more algebra than that. Now, solving an equation like that, I don't like having denominators around, so I'm going to go ahead and multiply, sort of cross multiply here and multiply by the denominator. So this tells me that x times 2y plus 1 is equal to 4y minus 3, so I can write the equation as 2xy plus x equals 4y minus 3. Trying to solve for y, so I want to get these y terms together. And I want to move everything else to the other side. So I'm subtracting 4y from both sides and subtracting x from both sides. Oh my. These don't combine though. I'm trying to solve for y, and these don't really combine because of that x on this term. They're not like terms. They are both y terms. So here's the deal with this. To solve for y, I have to sort of write this as a factored thing. They're both y terms, so I can factor out the y. Pretty tricky algebra right there. Now I can get y by itself by dividing here. So now I get y equals negative 3 minus x divided by 2x minus 4. That is my inverse function. I was able to get y by itself, and I don't have any weird plus or minus or anything. So that actually is a function that you could plug values into and stuff. That's my inverse function, though. F inverse of x is this thing. So that's normally what we do if we want the equation of the inverse function. If it's the right kind of function to have an inverse, and this one is, this process will work. You'll be able to solve for y with no strange stuff right here. Maybe it'll work, but you did get an expression, a function at the end right there that is the equation of the inverse function. Now, just to show what happened there before I wrap this thing up, let me run some numbers through this in case you're a numerical thinker. And this just looks like symbols wandered around all over the place. It doesn't look too constructive yet. But let's show how this works right here. If I do f of 2, my original function, now I'm going to do what f of 2 is equal to. 4x minus 3. So f of 2 is 4 times 2 minus 3 over 2 times 2 plus 1. That's doing f of 2. And that comes out 8 minus 3 over 4 plus 1, which is 5 over 5. I did pick something that comes out to a nice number like that. I got f of 2 to be just 1. So when the input is 2, the output is just 1, the original function. Those are going to switch places over here. So what I'm expecting to happen over here is if I do f inverse of 1, what was my output before? I'm going to make it into my input now and substitute that in. Watch what happens. I get negative 3 minus 1 over 2 times 1 minus 4. That's negative 4 over negative 2 comes out to 2. So this one, when I had an input of 1, I got the output of 2. So you can see the comparison right there. Input of 2 gave me an output of 1. Here the input of 1 gave me an output of 2. You could try some other numbers to that. They're undoing each other. They're inverses of each other. That's the concept we're trying to get to now. That's what we're working with in there. We're going to start to jump into logarithm ones in this. So I'm expecting some struggle with that because logarithms look a little weird, but they are the inverses of exponentials. And you got to try that out. You got to get used to the exponential functions a little bit. And then this inverse thing ends up being a logarithm. So that's explained pretty well. And of course, we want to get a little start on those. Those are the functions we're going to be working with through next week's work, getting comfortable with logarithms and how they work. So try some stuff out. Get back to me with some questions. Either the Lumen or the XYZ stuff, they both have explanation of this stuff. They both have practice problems. Whatever you like better on that. Work your way through those homeworks and ask questions as you go along. That homework's got to be on Monday sometime, and that's when the notes will come out on the new stuff. So I'm hoping to hear from some people with some questions between now and then. I'll try to stay in touch. So thanks for checking in. I can do more of these if I need to. We'll see how things go along. Send me some questions either in the Blackboard discussions or in email. Either way, I'll get back to you as soon as I can.